It conducts electricity only when light hits it, turns industrial glass a deep ruby red, and is deadly poisonous yet essential for human life.
I want you to start off today by just closing your eyes for a second and picturing something with me.
Always a dangerous proposition on this show.
Right, I know, but just humor me. Imagine a substance so incredibly potent that a microscopic speck of it, like literally just a speck, is keeping you alive right now. It is actively circulating in your bloodstream, and it's preventing your very cells from just crumbling from the inside out.
Wow.
But if you were to take just a tiny pinch too much of it, that exact same substance acts as a brutal, system-destroying poison.
Yeah, it operates as this flawless, biological, double-edged sword. I mean, it is the ultimate Jekyll and Hyde of the periodic table.
Exactly. And the crazy part is it isn't just biological, it's a shiny gray metal. Like if you look at the roof of a modern home, you might actually see this exact same element soaking up the sun, generating electricity for the grid.
Right, which is just wild to think about.
It really is. It's a material that somehow bridges this massive gap between, high-tech engineering and the most fundamental microscopic survival mechanisms of our own bodies. So today we're doing a deep dive into our sources on element 34, selenium.
Yeah, and to really understand how a single element can simultaneously power clean energy grids and act as this biological tightrope walk where one wrong step means disaster, we have to look at how it was even found.
Right. We have to go back to, 1817?
Exactly. 1817 to a sulfuric acid plant in Gripsholm, Sweden.
Which, the environment alone just totally sets the stage. Early 19th century chemistry was this wild, dangerous frontier.
Oh, absolutely.
You have these massive vats of acid, toxic fumes everywhere, and workers are just falling mysteriously ill.
Right. So Jan Jacob Berzelius, who is essentially one of the founding fathers of modern chemistry, he was called in to investigate this whole mess.
Which is a pretty big deal.
Yeah, it was. The workers were dealing with this strange reddish mud that just kept accumulating at the bottom of the lead chambers they used to produce the acid.
And it was making them sick.
Extremely sick. Whenever the workers interacted with this sludge, they developed severe respiratory issues, and they had this very distinct foul odor on their breath.
The sources mentioned it smelled like rotting radishes, which is just so specific.
Right, rotting radishes. And so the initial assumption, understandably, was that it was arsenic.
Because arsenic was a known contaminant in sulfur mining back then.
That was the logical hypothesis, yeah.
Yeah.
But Berzelius was, he was meticulous. He took this reddish sludge back to his laboratory in Stockholm, and he just went to work on it.
Dissolving it, boiling it, burning it.
Exactly. And he realized pretty quickly that he wasn't looking at arsenic at all. He had isolated a completely unknown non-metal.
Wow.
And when he finally refined it, he found that its most stable form wasn't actually that red mud, but this striking, shiny, gray metallic substance.
And the naming convention he chose for it is just so poetic. He named it after Selene, the Greek goddess of the moon.
He did, and he chose that name specifically because of its chemical behavior. See, a few decades earlier, another element had been discovered that looked and acted very similarly.
Tellurium, right?
Exactly, tellurium, which was named after the Latin word for earth, tellus. So because this new element was found right alongside tellurium and seemed to be its chemical twin, Berzelius named it after the moon, the Earth's companion.
I just love that. But if you look at the periodic table, selenium and tellurium belong to what chemists call the chalcogen family, group 16.
Right.
And the most famous member of that family is oxygen, followed by sulfur. But this is where the physics of the universe presents this really, really interesting paradox.
The abundance issue.
Yeah. Oxygen is the third most abundant element in the universe. It's in every breath we take. It makes up our water. It covers the planet. Yet selenium, sitting in the exact same chemical family, is incredibly rare.
Yeah, it is. And this gets into the mechanics of how the universe actually forges matter.
Right.
When elements share a family on the periodic table, it simply means they share structural logic. They have the same number of electrons in their outermost shell, 6, in the case of the chalcogens.
Which dictates how they react chemically.
Exactly. But it has absolutely no bearing on how easy they are to create in the universe.
Because creating an element requires stellar nucleosynthesis. You basically need a star.
Right. And oxygen is element number 8. It has 8 protons. So a standard run-of-the-mill star can easily fuse helium into oxygen right in its core. It's a very simple cosmic recipe.
Which is why oxygen is literally everywhere.
Yeah, but selenium is element 34. To cram 34 protons into a single nucleus requires an unimaginable amount of energy.
Like beyond what a normal star can do.
Way beyond. It requires the catastrophic death of a massive star in a supernova.
Wow.
So selenium acts chemically similar to oxygen and sulfur, but it is forged in these much rarer, much more violent cosmic events.
And I think that rarity makes its properties all the more fascinating, especially its relationship with light. Because selenium is a semiconductor, but it possesses this specific property called photoconductivity.
Yes, and this is the exact mechanism that made selenium one of the most important elements of the early 20th century.
Right.
Photoconductivity essentially means that a material's ability to conduct electricity changes completely depending on whether it is in the dark or exposed to light.
It's essentially like a reverse nightlight. Instead of turning on when it gets dark, this element only allows electricity to flow when the sun actually hits it.
Exactly. And if you zoom into the atomic level, you can see exactly why this happens. In the dark, selenium's outer electrons are tightly bound to the nucleus. They just do not want to move.
And electricity is just the movement of electrons, right?
So in a dark room, selenium is a perfect insulator. It completely blocks the current. But light is made of photons, which carry kinetic energy.
Right, little packets of energy.
Exactly. So when a photon strikes the surface of the selenium, it transfers its energy to one of those bound electrons.
It basically bumps the electron up into a higher energy state.
It pushes it right across what physicists call the band gap and into the conduction band. Suddenly, that electron is totally free to move.
Wow.
So the moment light hits the metal, millions of electrons are knocked loose, and the selenium instantly becomes this highly efficient conductor of electricity.
And this specific mechanism was the foundation for the entire modern office environment. I mean, specifically the invention of the photocopier.
Oh yeah, the early Xerox machines relied entirely on selenium.
The engineering behind that is just brilliant. You have a spinning drum coated in a layer of selenium, right? And inside the dark machine, the drum is given a static electrical charge.
Right, because it's in the dark, the selenium acts as an insulator and holds onto that charge perfectly.
Then the machine flashes this brilliant bright light onto the original document you want to copy.
And the white parts of the paper reflect that light back onto the selenium drum.
Right. And wherever that light hits, the selenium instantly wakes up, becomes conductive, and the static charge just bleeds away into the machine.
But the black text on your document, it absorbs the light.
Right.
So the corresponding areas on the drum stay completely dark, the selenium stays an insulator, and it keeps its static charge in the exact shape of your text.
Then you just dust the drum with black toner, which is electrostatically attracted only to those charged areas. You roll a piece of paper over it, heat it up to melt the toner, and boom, you have a copy.
It's amazing. You are essentially using a rare moon metal to translate shadows into electricity.
That is such a cinematic way to put it, and we still use that light reactivity today. It's why selenium is used in specific types of thin-film solar cells, converting sunlight directly into grid power.
Yeah, it's incredibly versatile.
But its industrial uses go way beyond just electronics, right? Like in glassmaking, selenium is used as this massive aesthetic problem solver.
Yeah, the irony of glassmaking is that the silica sand they use naturally contains iron impurities.
Right, you can never get perfectly pure sand.
Exactly. And when you melt it down to make glass, those iron impurities give the glass this unwanted murky green tint.
So glass makers just add selenium. In the right chemical compound, selenium actually acts as a deep red pigment.
Right. And because red and green are complementary colors on the color wheel, the red from the selenium perfectly cancels out the green from the iron.
The result is just crystal clear glass. It's literally an optical illusion baked into the chemistry of the material.
It really is. But, while translating shadows in photocopiers and canceling out colors in glass are elegant feats of engineering, they pale in comparison to what selenium is doing inside human biology.
Which is the core focus of our deep dive today. Because the exact same catalytic properties that allow it to manipulate electrons in a machine are what keep our cells from dying.
Exactly. In biology, selenium is categorized as an essential trace mineral, and the medical literature heavily emphasizes the word essential.
It's critical for a lot of things. Like it converts thyroid hormones from their inactive to active state, which manages our basal metabolism.
Right. It regulates the immune system. It plays a huge role in DNA synthesis and reproduction.
But its primary, most vital role, the really dramatic one, is acting as the ultimate cellular shield against oxidative stress.
Yeah. And to understand the shield, we have to understand the weapon it is defending against. We have to talk about free radicals.
Right, because oxidative stress is basically the biological cost of doing business. Our bodies run on oxygen, our mitochondria use it to generate energy, but the process isn't perfectly clean.
No, it's not. It produces metabolic exhaust, and that exhaust takes the form of free radicals.
And a free radical is simply a molecule that has an uncared electron in its outer shell.
Right. Electrons really like to be in pairs. It creates chemical stability. So when a molecule is missing an electron, it becomes violently unstable.
It's like a microscopic wrecking ball.
It really is. It will aggressively seek out another electron to steal just to stabilize itself.
It bounces around the inside of the cell. It will rip an electron away from a cell membrane, totally destabilizing it. It will tear into proteins.
And most dangerously, it will rip electrons right out of your DNA strands, causing mutations that can lead to cancer or accelerated aging.
It's essentially cellular rust.
Yeah, cellular rust is a perfect way to describe it. And if a free radical steals an electron from a healthy molecule, that healthy molecule now becomes a free radical itself.
Oh, wow. So it creates a cascading chain reaction of destruction.
Exactly, unless something steps in to stop it.
Which is where the antioxidant shield comes in.
Yeah.
Specifically, a family of enzymes called glutathione peroxidases.
Right. These enzymes patrol the cellular environment, hunting down free radicals and neutralizing them.
And they do this by offering up an electron to the free radical, basically pacifying it without becoming unstable themselves.
Yes, but the entire structure and function of these defensive enzymes is totally dependent on selenium.
Selenium sits right at the active site of the enzyme. And what's wild is that it's not a structural building block like calcium is for bones, where you need, pounds of the stuff.
No, not at all.
If calcium is the bricks, selenium is more like a highly specialized special ops agent. You don't deploy an entire army. You deploy one specific atom to the exact right location to neutralize the threat.
Yeah, because selenium is a chalcogen, it holds its outer electrons in a very specific configuration. It is large enough that it doesn't hold on to its outer electrons too tightly, meaning it can easily donate an electron to a free radical.
But it can also readily accept an electron back to reset itself, right?
Exactly. It acts as an incredibly rapid, highly efficient electron shuttle. Without selenium sitting at the core of that enzyme, the shield completely drops and the cell is just torn apart by oxidative stress.
Which naturally leads to a very dangerous assumption. Like, if this elemental special ops agent is the only thing standing between my DNA and catastrophic oxidative damage, I should consume as much of it as possible.
Oh, you definitely don't want to do that.
Right. The categorization of selenium as a trace mineral is a strict biological warning. We measure our required daily intake in micrograms, literally millionths of a gram.
Yeah, the recommended daily allowance is around 55 micrograms.
This is the razor's edge of biology we mentioned earlier. Your body's tolerance for selenium is incredibly tight. It is a necessary catalyst, but it is definitely not something you want accumulating in bulk.
No. And let's look at the dietary sources. You can get safe trace amounts from seafood, eggs, and meat.
Right.
But the total anomaly in the research, the food source that completely breaks the scale, is the Brazil nut.
This part blew my mind. The Brazil nut tree is one of the tallest, longest-living trees in the Amazon rainforest.
Right, and the soil in the Amazon basin just happens to be remarkably rich in selenium.
And these massive trees have these extensive root systems that act as hyperaccumulators.
Yes, they basically dredge the selenium out of the deep soil and concentrate it straight into their seeds.
And the concentration is so extreme that just 1 or 2 Brazil nuts provide the entire daily requirement of selenium for an adult human.
Right, eating a single nut is like dropping the exact perfect payload of elemental defense into your bloodstream. You are fully arming your glutathione peroxidase enzymes.
But if you sit down and eat an entire bag of Brazil nuts as a snack, which people do, you rapidly cross the threshold from defense to destruction.
Yeah, you trigger selenosis.
Which is acute selenium toxicity. And the mechanism behind how it destroys the body is just as fascinating and honestly terrifying as how it protects it.
Oh, the symptoms are brutal.
Yeah.
Severe neurological damage, extreme fatigue, a garlic-like odor on the breath.
Wait, that perfectly mirrors what Berzelius observed in the factory workers back in 1817.
Exactly. It's the exact same toxicity. And most visibly, your hair and your fingernails become extremely brittle and literally break off.
That is so weird. Why the hair and nails?
Well, the hair and nails symptom is actually the most revealing because it shows exactly how the excess selenium confuses the body's chemistry. Hair and nails are made primarily of a structural protein called keratin.
Right.
And keratin gets its structural strength from sulfur.
Because sulfur atoms bond with other sulfur atoms to create disulfide bridges, right?
Sure.
Which lock the protein structures tightly together.
Yes. But remember the periodic table? Selenium sits directly below sulfur in the chalcogen family. They look practically identical to the body's construction machinery.
Uh-oh.
So when you flood your bloodstream with way too much selenium, the cellular machinery gets confused. It accidentally grabs selenium instead of sulfur and tries to build keratin out of it.
It literally substitutes the building blocks.
Exactly. But because the selenium atom is physically larger than the sulfur atom, the selenium to selenium bond is longer and much weaker than a sulfur bond.
So the microscopic scaffolding of the protein just fails.
Right. The integrity of the tissue collapses, the hair snaps, the nails crumble.
That is wild. The very element that acts as a flawless shield for your DNA becomes a structural wrecking ball if the concentration is just slightly too high.
Yeah. The margin of error between peak biological defense and systemic toxicity is literally measured in millions of grams.
It really forces you to appreciate the sheer complexity of the evolutionary tightrope we are walking every single day.
Oh, absolutely.
I mean, we are totally dependent on an element that requires a dying star to be created, that we have to mine from the earth, and that our bodies utilize with absolute unforgiving precision.
It's an incredible story.
It really is. We've tracked this shiny gray metal from the mysterious red sludge in a 19th century Swedish acid plant to the spinning electrostatic drums of modern photocopiers.
Right.
We've seen it cancel out colors in molten glass and generate clean power on our rooftops. And we've seen it dive into the microscopic battlegrounds of our bloodstream, shuttling electrons back and forth to disarm the free radicals that are constantly threatening to tear us apart.
I think element 34 proves that in the natural world, the size of a footprint does not dictate the scale of its impact.
I couldn't agree more. Every time you step outside and the sun hits a solar panel, or every time you eat a mixed nut, you are interacting with this delicate, high-stakes balance.
Yeah.
But it leaves me with this lingering question. Our biology evolved to be utterly reliant on this incredibly rare moon metal, locking us into a daily, microscopic tightrope walk between life and poison.
Right.
If human survival hinges so completely on a few micrograms of a stellar anomaly, what other invisible elemental threads are silently pulling the strings of our biology without us even realizing it?
That is the beauty of tracing these elements.
Yeah.
The more we understand the chemistry, the more we realize how deeply tied our biology is to the fundamental physics of the universe.
Definitely something to consider the next time you see a Brazil nut.
Yeah.
Thanks for listening to this deep dive. Keep questioning the world around you.